So section 1.8, last section of the chapter on continuity. We're going to go into this a little more in depth than our informal definition from one of the previous sections. We're going to look at the definition of what it means to be continuous at a particular x value. So for the definition, we are looking at a function f being continuous at x equals a, and again we have that if and only if, the limit of f of x as x approaches a exists. So it's denoted by equaling L, which is usually a number. So this definition is going to imply three facts. If f is continuous at x equals a, the function evaluated at a exists. The limit as x approaches a of f of x exists. And parts 1 and 2 are equal. So we're going to look at example 1 and see if we can apply this definition. We have a rational function from our past. We have an opinion over there. Okay. So a little excitement going on. Is f continuous at x equals 2? So a lot of times we can visualize it and say most likely, but we need to apply the definition, and we want to do this a little more formally. So what we want to do is we need to show all three things. So I'll write that down. So we want to show that all three facts are verified. So I'll number them. So number 1, we want to decide, is the function evaluated at 2, do we have a number that we get that exists? So the rational function is not too crazy. Let's plug this in. We're going to plug in 2 every time we see the x. So a lot of times I like to show this if I'm trying to designate what my work is. So let's continue to simplify this. I'll go horizontally. 2 squared is 4, 3 times 2 is 6, then we have a 2, and then 2 plus 1 in the denominator is a 3. If we add up everything in the numerator, we should get 12 over 3, and then if we simplify, we're actually getting a number. And so we've just verified, yes, the function evaluated at 2 exists. It's actually equal to 4. So item number 1, we're good to go. Now, if we're looking at item number 2, we want to calculate the limit as x approaches 2 of our function. So I'll copy down the function x squared plus 3x plus 2 over x plus 1. And a lot of times if I'm noticing that it's a rational function, you know, the first thing I always look at is if I were to plug in 2 to the denominator, it does not make it 0. So we can continue with plugging using direct substitution. Plugging in 2 to the function is actually us evaluating the limit. So if you see what we just did right here, it looks like it's going to be the same result as criteria number 1. So just be careful whenever you're asked to calculate the limit. We do see that we have an exact case from item number 1, but it's not always the case depending on what is x approaching. So be careful with that. And if we want to further clear up, is this continuous or not, is steps 1 and steps 2, or item 1 and item 2, are they equal? And we can definitely see, yes, there is a match going on. And the way I always justify this, and this is mathematics, we are going to clearly state the function evaluated at 2 is equal to the limit as x approaches 2 of the function, and that's justified by parts number 1 and 2. So if all 3 criteria hold, we can now conclude, therefore, the function is continuous at x equals 2. So we have just proven that fact. So that's nice. Few questions along with example 1 we want to kind of inspect. Sometimes we're going to be asked about the function being continuous or having limits exist at different values of x. So I like to point out part B. We'll notice that here x is approaching -1. So if we, again, inspect our denominator, if you were to plug in -1 to x plus 1, we would have an issue because we would have a denominator being 0. So just kind of a little note to ourselves, f is undefined at x equals -1. So we could not use direct substitution to try to calculate the limit. We're going to see if we can try a few math tricks first. Let's see about, usually factoring comes to mind. So let's go with rewriting the limit as x approaches -1, and then I'll rewrite what the function is, x squared plus 3x plus 2 over x plus 1. I'd like to see if maybe the numerator factors, maybe the denominator might be able to be canceled out. And so we do have a trinomial. And I want to emphasize we have not calculated the limit yet, so we're continuing to write the limit notation. All we are doing is modifying what the argument is. So if we're looking at factors of 2 that add up to 3, this is a nice factorization. We have x plus 1 times x plus 2. And right away we see, x plus 1 over x plus 1 divides out, and that's fine because the function is not defined at x equals -1. So then we're still left with, again, we have not evaluated the limit yet, so we still need to write the limit notation. The limit as x approaches -1 of x plus 2. And here, if you look at what the argument is, if it's a linear argument, if you were to plug in -1, you're going to have some definition there. So we can use direct substitution finally. So now if we were doing this, this is where we can get rid of the words limit. We're actually substituting in -1 plus 2, and the answer to that is 1. And so we actually calculated a real number. So the answer to part B is yes, the limit does exist. So you want to be careful. The difference between part A, item number 2, versus part B, whether something's defined or undefined at the particular x value. And so the other question would be, if we want to kind of look at the continuity, is f continuous at x equals -1? So we could kind of see, if we want to go through this, we're going to go through the 3 criteria. Looks like part B has taken care of item number 2, but let's kind of do a quick check. Does the function exist at x equals -1? I know just from part B, we did know that the limit as x approaches -1 of f of x, it does exist. So we know that for sure from part B. But I want to check criteria number 1. And then we want to check to see if it's equal to criteria number 2 to really define the continuity. So remember, if we're looking at what's actually happening at x equals -1, we've already kind of answered it in part B. F is not defined. So if you were to try to plug in -1, you get an undefined expression. You would not be able to say that the function evaluated at 1 exists. So if you can't prove item number 1 and item number 2 are equal, then we can say the function is not continuous. So you definitely want to see if you can state this. And I know back in pre-calculus, a lot of times when we're asking these questions, we were kind of saying, well, we can tell something's continuous if we can move our pencil along the curve. And as long as you don't have to ever lift your pencil up, then it's considered continuous. But in calculus, we have to take a more formal approach, and we actually have to show what this means. So be careful as far as caution is concerned. Proving the limit exists is necessary, but it's not enough. Not enough to prove continuity. And that was the example we're trying to demonstrate if we're looking at part B versus part C. Remember, we only talked about item number 2 in the continuity definition, but you need to verify that all 3 facts are clear. So a little bit more practice with those formal proofs. We're kind of going to be looking at those in terms of you being able to justify them in writing. And I know WebAssign does have a little bit of practice there, but I always recommend handwriting them out. So just kind of a tag onto continuities. We're going to kind of go over the 3 types of discontinuities that we could run into this class. We're going to talk about, let's see if I can draw a few examples. I always like to visualize them first to see what's going on. So let's say we have a function that appears to have a hole at x equals a. And we could say, well, it looks like the limit could exist. And the function evaluated at a is at a different part. We'll say that's what f of a is evaluated at. And so if we want to talk about the fact that we're looking at discontinuities, if we want to reason behind this, the function evaluated at a, it does exist. We actually see a pair for it. It's a y value there. And also the limit exists. If we kind of go over, as all the x values are approaching a from the left-hand side, it appears that the y values are rising to L. And the other way around, if all the x values are approaching a from the right-hand side, the values of y are dropping to L. So just kind of summarize this. We do have f of a. Whoops, let's see if I can be a little clearer on that. The function evaluated at a and the limit, they do not match. We do know that the limit exists, but in order to be continuous, you have to match all 3 criteria from the definition. So we will deal with this in a second, but this would be kind of a common type of discontinuity you may see. And we call this, just so that you know, we call this a hole a lot of times. And you've probably dealt with them when you were dealing with rational functions in pre-calculus, but we'll definitely review them. The next type of discontinuity, let's say we have a function. Let's say we kind of have the same idea. where we appear to have something going on at x equals a. In this case, if we were defining this sort of idea, this is a case of having a jump discontinuity. And we can see that, yes, the function evaluated at a, it does exist. We can see it that it's up here somewhere. And the limit, we play around with this a little bit. I'll just call this, well, I won't call it a number yet, but I'll just say, oh, maybe it's some y value. Now, we'd have to be really careful, because if you are approaching a from the left-hand side, you are going to have the y values rise to the limit, and I'll denote it as limit with a subscript of 1, L1. But the issue is the limit from the right-hand side. If you're actually approaching from the right-hand side, you're kind of looking at what your y values are doing, and they are not approaching L1, they're actually approaching the function evaluated at a. And so when you don't have the limit on the left match with the limit on the right, at this point, we have a limit that does not exist. We use the D and E notation. So that's something to play with. Just kind of look at the difference between having a hole versus a jump. And then another one we have dealt with, I'll go over the last type. Let's say we have, usually rational functions or piecewise functions kind of follow these issues. But let's say we have something, you might recognize what it looks like. Let's say we have a vertical asymptote. I'll label that for you. And if you kind of play around with talking about the limits, it is clear that the function evaluated at a, it does not exist. So we can already know right away it's not continuous. But if you want to speak about this in terms of limits, if you were approaching a from the left-hand side, your y values seem to be rising up higher and higher and higher. It looks like they're approaching infinity. And a lot of times we use this as nice notation to designate what is happening to the y values. But if you remember, we can't really say the limit exists if it's equal to infinity, because infinity is not a real number. So if you're kind of looking at it, even when you're approaching from the right-hand side, yes, the y values are still rising up and they will reach positive infinity. But in the end, we would have to say that the limit does not exist. And the reason is because we can denote positive infinity as the limit, but it's not a real number. So we have to be extremely careful here. And this is what we call, sometimes when, instead of saying vertical asymptote, you'll hear people refer to this as an infinite discontinuity. And hopefully the fact that you're kind of looking at, it looks like the function approaches positive infinity or maybe negative infinity, that should probably give you a clue as to why they would name it something like that. So we're going to be running into these and analyzing these a little bit, but let's kind of go over little definitions. What I like to think about, they're gonna apply to these discontinuities as, they're going to ask you questions. Are these removable? Are these non-removable? And the easiest way I can explain this is if you're able to patch the hole in your particular function, you can consider this a removable discontinuity. So if we look at all three cases that we have gone over, it appears that the first idea, the actual hole part, we have ourselves a removable discontinuity. And the reason why is we can patch the hole. Nice little single value you can use. And a little note with removable discontinuities, the limits, remember, it exists. That's something that's helpful to us. Now the other items, the jump, the vertical asymptote, or the infinite discontinuity, what's going on? If you try to look, and I'll look at where the gaps are, we have a hole, and then we also have a lot of gap going on with the jump. There's no way we can patch that part with a single function or a point. Similarly, you cannot patch up a vertical asymptote. The function is never defined there. So we call these cases non-removable discontinuities. See if I can write that down. There we go. So non-removable discontinuities. And kind of one of the heads up on some of those is you'll kind of see, well, it's not really removable, but a little note on this is that the limits don't exist. So it kind of gives you something to look at. So we're going to apply this idea to the next few examples and then kind of give a little bit more analyzation of all these either rational functions or these piecewise functions. So let's go over this. We'll look at example 2. They're going to ask us to find all discontinuities for the rational function f of x equals x squared plus 4x plus 4 all over x squared minus 4, and classify them as either removable or non-removable. Now, a lot of times from our pre-calculus class, we can automatically determine what they would be if we know if something's a hole or something's a vertical asymptote. And you could guess who's removable, who's non-removable based on that definition. But we need to justify why they are using techniques of calculus. So it's gonna be a little different coming on here on out. But I will go over both just so that we get a good idea of how things are connected. And just kind of give you an idea, just note to you that we do have ourselves a rational function. And little review, and we've seen this actually when we've been dealing with limits, but rational functions are discontinuous when the denominators are equal to 0. And so if we look at this a little clearly, we can look at the denominator, this x squared minus 4. Sometimes when it's more complicated than just a single value of x, we can actually set ourselves up a mini equation. X squared minus 4 equals 0. And you could solve it. It looks like a quadratic equation. You can solve it using difference of squares or the square root property, but I'll show you just by factoring. We have x plus 2x minus 2. So we're actually getting two values, x equals positive 2 and negative 2, that make the denominator 0. So we can say, using some pre-calculus, therefore, the function is discontinuous at these values, x equals negative 2 and x equals positive 2. Now, with pre-calculus, they call this, maybe it's like a practical approach, but I'll label it just so that we have this for yourself. So pre-calculus, a lot of times when we were kind of determining this, we would actually simplify the function writing this over for you so that we can analyze it. So we would simplify x squared plus 4x plus 4 over x squared minus 4, usually done by factoring. So we'd kind of say, okay, we'll see if we can factor the numerator, and I'll work horizontally to save some space. Looks like the numerator factors of 4 that add up to 4. And also the denominator, another difference of squares. We just kind of dealt with that earlier. And we kind of see that whenever you end up dividing out a common factor, we used to call these wholes. So a little note there. Anytime we divided out a common factor, we would note that this is a whole. X plus 2. And actually, let me write that a little nicer for you all. So we're dividing out the common factor x plus 2. And so that would tell us, that would imply that x equals -2 is a whole. And we know that wholes are removable. But once we simplified the function, what would happen is we would take the new version when everything is divided out. We would say, okay, we have this new function f of x equals x plus 2 over x minus 2. What's the resulting factors? And we can't just leave it at that. We had to remind ourselves when we do this, we have to really denote that x is not allowed to be -2. But at this stage, you would see, okay, we're going to look at the resulting function, and then we could also say, if we were set to set the denominator equal to 0, this would talk about what we talk about with vertical asymptotes. So we would have x equals 2 is a vertical asymptote. I think that's like about 2 weeks worth of material in college algebra or pre-calculus, and we just did it in 2 minutes or so. But if you know that you have a vertical asymptote, then you can go back to your definitions, and we notice that, you know, vertical asymptotes, you can't get rid of them. We actually have a non-removable discontinuity. So that was fine and great when we were in pre-calculus, but we are going to utilize the techniques of our class. It's always nice to think back to your past and you can justify or give you a heads up of what you're going to see, but I want to remind you of the formal approach, and this is something you'd want to show on a quiz or test so that you would get all of your credit. So calculus techniques. And this is the formal approach. Oh, let's write that a little nicer. Okay, so with the formal approach, a lot of times what we like to see is we want to talk with limits. So we're going to take our particular function and we're going to talk about what's happening at -2 and what's happening at +2. And when we're dealing with limits, I'm going to deal with the reduced function. So if I took the formal approach and I want to talk about the limit as x approaches -2 of my function, we'll write a little bit more in relation to our problems. So we have x plus 2 over x minus 2. And remember, since we're not defined at x equals -2 in our previous function, but we were able to divide out a common factor, if you look at plugging in -2 to the denominator at this point, you're going to be able to use direct substitution to calculate that limit. So we can do that. So we're going to plug in -2 for x. And this is where we get to get rid of the limit notation because we're actually using the direct substitution. We get ourselves 0 over -4, and that calculates to 0. So we just calculated that we have the limit exists. We got a real number. So we can say that f has a whole at x equals -2, 0. And by the way, x equals -2 is removable. So as soon as you find that the limit exists for that particular value in question, notice that from the criteria of what we defined earlier, you can say, okay, limit exists, it's patchable, it's a removable discontinuity. So now what I want to do is look at the other version. I'm going to have to move over to the side. I ran out of room here. Let's go this way. And let me see if I can keep this again with the formal approach. And I want to look at so now let's look at what happens at +2. So let's calculate the limit. I'm going to move over right here. The limit as x approaches 2 of our function, as x approaches +2. So we'll be looking at the limit as x approaches 2 of x plus 2 over x minus 2. And then this is the case, again, if you look at your particular denominator, if you were to plug in x equals 2 to the denominator, we would have an issue. And that's kind of what you always want to make sure of. X equals 2 makes your function undefined. So before we can talk about, does the limit exist, does it not exist, there's nothing I can do with the particular argument to simplify it further. So I'm circling it in purple. There's no nice things I can do to it like factor, rationalize, combine over common denominator. So one of the techniques we learned, if we couldn't play with the denominator algebraically, we would try, maybe approach this in a way looking at the one-sided limits. So what I mean by that, if we do look at the one-sided limits, let's calculate the limit as x approaches 2 from the negative side, x plus 2 over x minus 2. And the limit as x approaches 2 from the positive side, x plus 2 over x minus 2 is still the argument. And so just remember with this notation from earlier, whenever we're looking at the 2, and it looks like the negative sign is in a spot of an exponent. It's not really accurate to say that, but that's what it looks like. We would be speaking about numbers to the left of 2. So if I were on a number line and I want to pick a number to the left of 2, but I want it pretty close to 2, one of my examples I could choose, let's try to plug in maybe x equals 1.9. That's a number a little bit less than 2. It's pretty close to 2, not too far away from 2. So if you were to plug that into the function, and this is kind of more of an intuitive approach, but it serves our purpose well in this class. I can approximate the limit. So I can use direct substitution for the x values. So that would leave me with, we have like 1.9 plus 2 over 1.9 minus 2. And if we were to calculate that value, we should have about 3.9 over a negative number, negative 0.1. And we're going to use an approach where we really want to analyze what's happening with the numerator and what's happening with the denominator. So yeah, you can calculate the value, but it's not really useful in our terms of trying to figure out what the limit would be. So what I like to look at whenever I do this approach, where I'm choosing numbers that are pretty close to our undefined number, is I kind of want to note to myself when I'm looking at my expression, let's first pull out the negative sign. So we have this negative sign that was already in the denominator. Let's just pull it out to the front so we don't have to deal with this any longer. So we do have a negative number. Well, yes, that's negative, Leica. We told you already. Okay, so what we're going to, let's look at 3.9. And you might want to agree with me, hopefully on this one, that 3.9, it's a number close to 4. We'll go with it. And what I'm looking at 0.1, I'm looking at 0.1. If we're comparing it to the number 4, it's a really small number. Now, if you divide a number close to 4 by a really small number, and feel free to use your TI to play with this, and this is where we kind of talk about analyzing. A number that's relatively big divided by a number that's really, really, really small ends up being a really big number. So you're actually going to get a really large number. And I'm using this in terms of intuition. We could actually do the division and find out, but then we'd have to understand, you know, how big is big? How do we deal with that? But what I'm trying to get at is whenever you want to talk about a really big number, usually people refer to that as infinity. So if I'm looking at the limit as x approaches 2 from the left-hand side, I still have my negative, and a really big number, another way to talk about it would be maybe talk about it as infinity. We're going to approach that a lot more in these problems. Let's look at the other side just to make sure. We're kind of getting it. And this type of approach does help when we're analyzing. Let us look at the limit as x approaches 2 from the positive side. And let's refer to ourselves, what does that mean again? I see that notation a lot. It's a one-sided limit. And if I'm speaking about that, we are actually looking at numbers to the right of 2. And if you want to pick a number to the right of 2, an example, that might be, we want it pretty close to 2. So 2.1 would be a good candidate. You don't want to choose 10 because you're not speaking about the neighborhood of 2 anymore. So if we were to take 2.1, let's write this out a little nicer. So let's say we tried x equals 2.1, and we tried to plug it into our function. We can use direct substitution because the function's still evaluated, still exists at this number. So we're going to take x equals 2.1, plug it in for x, and we're going to have an approximation because we're not really clear. We don't have the actual limit, but we have an approximation. If we kind of play with this, we have 2.1 plus 2 and 2.1 minus 2. And if we want to do a little bit of the calculation there, we are going to get a value, we should have about 4.1 over 0.1. And with the same sort of argument, if we're going to look at what 4 really means, first of all, you know, positive divided by positive is positive. We're going to get a number close to 4, 4.1. And 0.1, if you compare it to 4.1, we can say it's relatively small. So we say really small number. Now, when we play around with divisions, if you have 4 divided by a really, really small number, you're going to get a really big number back. And if we really use those words, really big, I know that's not so formal in calculus, but intuitively, a really big number for us would be positive infinity. So if we look at what's happening on the left side of the 2, what's happening on the right side of the 2, in order for the limits to exist, they have to be equal. And the fact that you have infinities, remember, they're not real numbers. Negative infinity is not a real number, neither is positive infinity. Since the limits do not exist, we're going to look at ourselves having an infinite discontinuity. And usually when you get infinities for your limits, there's that vertical asymptote coming back at you. So there might have been a formal definition from pre-calculus, but now calculus gives us an idea of why this is the case. So we would say f of x has an infinite discontinuity. At x equals 2. And if you're an infinite discontinuity, i.e. a vertical asymptote, you're non-removable. So this is what you would want to do if you were using calculus to prove that you have a discontinuity. So look into that. And then we can go back and use a little bit of our knowledge of the graph to help us justify the results that we just got. So kind of going back with the continuities, we talked about having a whole, removable, and we talked about having an infinite discontinuity. So this is where I like to look at the graph. You can use your TI to justify this. I just blew up the graph really large so that we can see this a little bit nicer. So we're going to look at what's actually going on. Let's kind of remind ourselves, we're looking at f of x equals x plus 2 over x minus 2, and just kind of reminding ourselves that we already had decided that x was not allowed to be negative 2. We can justify that. Let's see if I can make my scale a little bit nicer. I'm gonna really blow this up. So I should have like 1, 2, 3, maybe 4. -1, -2, -3, maybe -4. We'll make these 1 and -1 from here on out. So when we're looking at our particular function, if we're kind of using, you know, what's happening at 0, we should get -1. Feel free to inspect with all your points if you need to. I'll draw this in blue still. And we already figured out we had a whole at -2. And we can kind of see at +2, there's a vertical asymptote. Now, if you're kind of playing along with this, we did not quite address what's happening to the function, but if you do pick a lot of values of x, you're going to see that there's some sort of leveling off issue going on. And I will, I'll draw this in for you in green. But if you were to use your TI to kind of inspect the function, it appears that we're getting the function to look like this and like this. And let's justify this y. If we know we have what is happening as x is approaching 2 from the negative side, we talked about the limit going to -infinity. We can see the graph shoots down to -infinity. And again, just continuing on with this vertical asymptote. As your x value is approaching 2 from the right side, we see that our graph is shooting up very, very fast to +infinity. That's kind of justifying what's going on. Other cases, when we analyze our function, we might be asking ourselves, what's going to happen as x gets very, very large? So sometimes they talk about this as long-term behavior or behavior in the long run. So if you want to analyze this just a little bit, and we do have techniques about talking about a horizontal asymptote, comparing the degree of the numerator with the degree of the denominator. But at this point, we don't really have to go into depth. I kind of want to use the arguments we've been playing with the words really, really big number, small number, etc., to kind of really approach this. So we're kind of looking at the far ends. And so an intuitive way to approach this type of function, and again, if you have the graph of it, you can automatically kind of see what is going on. But if you don't have a graph in front of you and you really want to inspect, what does it mean to be very, very large? I would say beyond our actual coordinate graph that we have, let's go crazy and let's try what happens when x equals positive 100. So we can go back to our function, just make sure we know what it is. F of x is x plus 2 over x minus 2. I'll write it down just so that we have that. And if you were to plug in 100, we should get 100 plus 2's. 102, 100 minus 2, 98. And when you kind of play around with these, when we kind of look at the numerator compared with the denominator, their numbers are relatively close. So when the numbers are relatively close to each other, we can talk about them being about 1. And technically it's slightly over 1 because you have an improper fraction. So actually it's slightly over 1. But at least we have an idea of what's going on with why would we have a horizontal asymptote. You can go crazier. What happens at x equals positive 1,000? What do we get? We should have something like a number that's, 1,002? We have 998 in the denominator. And again, when you compare the numerator with the denominator, they're very, very close to each other. We can say, hey, if they're very, very close to each other, they're still about 1. So it's telling us what our y values are looking like. So this is kind of on the idea. If x gets really, really large, let's go super crazy. We would expect that we should get a number that's also very close to 1. So it's kind of like if you were to win $1 million, but the bank forgets 2, are you going to complain? Pretty close no matter what. So that's the idea behind this intuitive approach. Similarly, we're talking about x getting very, very large. So this is telling us why is our function approaching the number 1 as we're going very large in the positive direction. If you get very, very small, on the same sort of argument, just so that you can also inspect it on your own. If we talk about x getting very, very small and we want to say what happens at x equals negative 1 million, you're going to get, what if you have negative 1 million plus 2? I think we're going to get something like negative 999, 998. Negative 1 million minus 2 is negative 1 million and 2. And negative divided by negative gives you a positive number. But when we kind of look at what's happening, we have a proper fraction. So these numbers are very, very close to each other. Same number over same number is about a 1. But we should have the fact, because it's a proper fraction, we should have something that's slightly less than 1. But in essence, this is justifying why do we have a horizontal asymptote? And so by the way, just kind of sometimes we can label that the horizontal asymptote is the equation y equals 1. So as x is getting very, very small, the function seems to be approaching a certain y value, and that's the justification behind those. So I encourage you to play around with this. I like playing with the intuitive definitions of plugging in really, really small numbers, really, really large numbers, and it really does help me understand why are we getting close to numbers no matter what we plug in. Also kind of go back and eventually we're going to, you know, a lot of calculus talks a little bit about the concept of really, really big number, really, really small number. And I like that language because it makes it more reasonable in my mind. There are shortcuts we will run into later, but I'll leave it at that. So having fun yet? We're almost there. We're going to look at a few more examples. We have example 3 and example 4. And we're going to talk about the idea of trying to patch up a piecewise function. And I know they don't really refer to it in that manner, but this is how I like to look at it. This is kind of where they're asking us, is there a value of k, so we're kind of looking at our k right here, that makes the function continuous everywhere? So we always ask ourselves, we could talk about what we already know. You can break up this piecewise function into 3 different pieces. We can look at what happens if, let's look at this, what we know. A little note to the side. You can look at all 3 pieces. So the first piece, y equals 10. Excuse me, x plus 10. We know that's a line. We're good on continuity. Lines are fine. If we were to play with us having a number, k, y equals k, let's just say, for instance, y equals 5. Might as well. We know that that's also a horizontal line. There's no problems with continuity in that case. And then if we look at y equals 5 minus x minus 3 squared. I won't even write it down. I'll just verbally speak about it. This piece right here is actually a parabola. So we really have no problems with continuity when we have parabolas. So we're probably guessing it will be okay. There'll be a value that we can choose that will work out. I don't know if it's going to be 5 or not. We'll look for it. But generally, when they ask the question, is there a value of k that makes f continuous everywhere, we might be concerned about what's happening at that value. So that's kind of where my highlighting comes into place. Question, what is happening at the domain x equals -3? Can you fill in k to connect the 2 pieces? So we have a line as x plus 10 and a parabola, 5 minus x minus 3 squared. And the answer to this, we're going to discover, if there is any issues, then what happens is they occur at the endpoints of the domain. So that's kind of important to note. If there are any issues, and I'll be a little more formal here. I'm going to say may. Not always happening that they occur at the endpoints of the domain, but most of the time it does. So they may occur at the endpoints of the domain. And so if I'm playing with my piecewise function and want to talk about continuity, limits are the first thing I like to look at. We already know if you were to plug in values, you plug in something to a line, it's going to be continuous. You plug in an x value to a parabola, it's probably going to be continuous. It's the k that we're really interested in. So limits are where we're going to look at for our discussion of continuity. It's the second criteria. So I'll formally say this, that we want to look at the one-sided limits. Mainly because they're broken up into a few different pieces. So I'm really hovering around x equals -3. I don't really know what's going on because I don't know what k is. So I'm going to look at two positions. So let's look at the limit. As x approaches -3 from the negative side of your function. And when you are looking at a piecewise function, you're going to look at the domain to decide what piece are you going to write in for your f of x. So remember what the notation says. If you're looking at the one-sided limit and you see a little negative sign, I'll highlight it in yellow. That's looking at the function on the left of all the x values, the left of the -3. So it looks like you'd be choosing the x plus 10 piece, and we actually want to inspect this a little bit further. So we can say that's the same thing as limit as x approaches -3 from the negative side, of course, of x plus 10. And I'll write this in red just to make it stand out, just so that we can see that we are choosing that piece because we are looking at values of x that are to the left of -3, and that's what the domain is telling us. And I'll erase the highlight just to make things a little bit more readable. So if we're going to approach this, what we can do is we could say, well, if we are looking at a linear function, we know that there's no issues of direct substitution. The function is defined everywhere. If you want to pick x equals -3, direct substitution, you are allowed to. So the result we should get if we are plugging this in, it's around -3. -3 plus 10 is going to give us a +7. So we have a one-sided limit there. Now, I want to look at the limit as x approaches -3 from the positive side of your function. And you'll see similarly, if you really want to analyze this, if we look at values to the right of -3, we would be looking at the domain x is greater than -3. So that's going to tell us to apply the parabola right here. If I'm using limit notation, it's written a little bit differently. I like to make sure I'm being formal. Whenever I use limit notation and I have more than one term, I like to include the entire argument in some sort of parentheses. This time I use brackets because I already had something that had parentheses already. So now we know no matter what, we can play with -3. We already have a parabola. We know it's not going to be undefined anywhere. We can use direct substitution. We can plug in -3. And actually, I'll do this by hand because it's a little more complicated than -3 plus 10. But using direct substitution, we have 5 minus -3 minus 3 squared, or 5 minus a -6 squared, or 5 minus 36, which is -31. Now, when we do the comparison right here, if the limits were the same, we would be okay. We would have an existing limit. But when we do the comparison, we see that the limit of f of x as x approaches -3 because we have different values, it does not exist. And that means if the limits don't exist, you have some sort of jump discontinuity. Remember, we didn't get infinities for these values. We got actual numbers for each of the sides. However, they have to match for the limit of the function as x approaches -3 to actually exist in general. So if we're kind of playing with this, you can kind of look at, well, if the y value is 7 and the y value is -31, that is a jump. You're not going to find a single value of k that's going to be able to connect those two pieces. They're not approaching the same limit. So we for sure know we have a jump discontinuity. So f has a jump discontinuity at x equals -3. And because you can't patch something that far away with a single value, no value of k, want to answer the question, no value of k can make f continuous at x equals -3. So you could take my word for it, or you could kind of make a graphical argument, which is a lot of times what people would like to do sometimes. Sometimes you prefer to make graphical arguments instead of writing all this out, but we really want to make sure that we are inspecting the limits from each side to get full credit. But if I'm kind of looking at maybe kind of playing with a few of them, see if I can graph our actual function. Let's graph the two pieces. We were to graph f of x plus 10. So I'll give you an about. So a little graphical argument. The way we're looking at our two pieces, y equals x plus 10. We know that it's not quite defined at 3. So let me kind of, I should say -3. So I'll mark it on the function. Y equals x plus 10. And where am I getting this? I'm getting this from our function. So let me make sure that I'm not making this up. We have the function is x plus 10 if x is less than -3. So it's a line, and we kind of look at it. It should be where it's kind of hitting about 7. So I can mark it about here. Got ourselves a straight line. If we look at the parabola, 5 minus x minus 3 squared, or x is greater than -3. When we kind of look at what's actually happening at -3, we see like the limit, we have a -31 somehow. So that's really far down here somewhere. And I'm not being too exact. Of course, you can inspect this later, but I do have a parabola, and I know based on the negative in front of the function, we do have something that is facing downwards. So then when you kind of look at the differences of the two y values, we have a y value here, a y value here. There's impossible. You cannot close that gap with a single number. So that's your graphical argument. And a lot of times, some of you may even do that first before you even start the idea of justifying this, so that you could kind of have an idea of what it's supposed to be. Kind of a trick, huh? Now, if you were to have a limit, like what if, right? So what if, we had our function, let's suppose we had something happen. Let's say we had the limit as x approaches -3 from the negative side. Let's say it was equal to, we already knew it was 7, but let's suppose you got a matching limit approaching to the right. You would have a case, and again, this is a what if. This is not applicable to what's happening, but you would have a case of when we kind of draw our graph, we have, let's see, right where my -3 is about. We still have our line going on. But if the limits were to match, what's happening is you would have the parabola supposedly would be doing something where it automatically connects and you'd be able to patch whatever that hole is if it would be the k. So if k was equal to the limit, that allows us to patch that hole. So I mean, just kind of go through these. It is intuitive. If you actually graph it for yourself, you can see like when do you have a single value and when do you have a jump, when do you have a hole versus a jump. So play with it. I know this is really involved, but you can kind of take this time, rewind the video a bit, do a few problems from WebAssign that apply to it, and that should help you out. So that's kind of discussing what happens if they ask, is there a single value that makes the function continuous everywhere? Example 4, a little more exciting. Look at this part. They're asking, is there a value of a and b that make the function continuous everywhere? And in what they're trying to refer to is when you look at it, in other words, would we be able to find a line that passes through the two holes in the function? So you could kind of analyze this graphically just for a bit. You know, if I actually have the same function here. So y equals x plus 10. What's happening at -3? We already kind of played with the fact that it was some sort of hole. We have a linear function. And then at 2, let me make this a little prettier so that we have this. I know you can use your TIs to inspect or sometimes Desmos. But if we have x equals -3, I'll play around with this a bit. Limits at 7, we have something going on here. At x equals 2, I'm only saying this based on my 2 endpoints of this value. It looks like I have a constant function, y equals -3. So it appears that we have something here. Constant functions are horizontal lines. So the idea, if you inspect what's going on, you know, theoretically, we should be able to find a line through those 2 points. And you can actually do this if you know the ordered pairs. You can use a little algebra to think about this. But we do want you to use limits. We're using theory of calculus to help us figure this out. So again, whenever we are dealing with piecewise functions and we're trying to figure out what's happening at these endpoints of the domain, we're going to be dealing with the one-sided limits. So example 4 is kind of another extension of what would happen, like if example 3 was more complicated. Now we can see what's probably going to happen. We can probably figure out what's going to be the answer to this question. But I want to justify it with calculus, a little bit of limits, just to get you guys comfortable with being able to do this. So if we want to look at one-sided limits around the x value -3, I'm going to try to label this for you. I'm going to say left limit, limit as x approaches -3 from the negative side of f of x. And again, we remember kind of similar to example 3 that you're able to plug in the piece that applies to the x values that are to the left. So that should be x plus 10. And from example 3, we already calculated this to be, by direct substitution, we got ourselves A7. no problem there. Now, if we look at the right-hand limit, as x approaches -3 from the positive side of the function, we are now looking at the, yes, we have to calculate the other side. Okay, so we're going to look at the ax plus b part. Now, remember, we're looking around the -3. So we are looking at the ax plus b. So the limit as x approaches -3 from the positive side, we would have to plug in, think about what we're looking at, ax plus b. And with direct substitution, if you were going to plug this in, really quick, we don't know who a is, we don't know who b is, we know who x is. So x is getting substituted with a -3. So that will leave us with -3a plus b. So we're not quite aligned, we're just figuring out values of a and b. Now, in order to be continuous, I like to write it out. We could talk about this verbally, but it's nice for formal notes. Your limits as x approaches -3 from the negative side of your x plus 10 has to be equal to your limit as x approaches -3 from the positive side of ax plus b. That's the definition of the continuity coming in. Criteria number 2. And so what you're going to have for yourself, if we're going this route, we already calculated the limit 7 is equal to -3a plus b. So the limits that we calculated, the one-sided limit, should be equal if the limit exists at everything. So I'm going to come back to this later, but you're going to probably guess what we might see. I looked at the endpoint limits around what's happening at -3. The next thing I want to look at are the one-sided limits around the other endpoint of the domain too. So that's what we're looking at right here and right here. So let's do that. Just be patient with this process. It's a really good way to analyze limits and try to understand the concept behind all of this. So the left side, if x is approaching 2 from the left side, well, let me write that a little nicer for you. You have to decide what piece you're going to take. If you're approaching 2 from the left side, you're going to be taking the ax plus b piece, according to what the domain is talking about. So I'll restate that. The limit as x approaches 2 from the negative side. So instead of writing f of x, we have that particular piece. I'll write it in red so you know where I'm looking at. And it is a line, some sort of form of mx plus b. So we can use direct substitution to substitute in for x, and we would be plugging in 2. So if we were to calculate this, we should be getting 2a, so a times 2 is 2a, plus b. And then now if we look at the limit as x approaches 2 from the positive side of the function, we have to decide what piece to take. We have the limit as x approaches 2 from the positive side. That is our -3. And the limit of a constant always spits back a constant at you. So we already have a number for that. And then with the same argument, in order for the piecewise function to be continuous at x equals 2, we would have to say the limit, well, Why am I using the full word? I've been writing a lot lately. I keep using the full word. Okay, here we go. The limit as x approaches 2 from the positive side has to be the same as the limit as x approaches 2 from the negative side. And actually, I'll put the negative side first. So the limit as x approaches 2 from the negative side of ax plus b must equal the limit as x approaches 2 from the positive side of 3. Should be negative 3. And we already calculated those, just so that you guys can see. We had the 2a plus b. 2a plus b, there we go. And negative 3. So my friends, does this look familiar from our past algebra classes? And this is what we mean about calculus pulling in all the things we've ever learned. We actually have ourselves, the 2 box items that I have, actually have ourselves a system of equations. So our job, solving these system of equations, and I'm going to move over. Yeah, I don't have that much space. I can write on the page, but I like to kind of show you where I'm getting at. So if we solve this system, I know you're used to using a lot of x and y's, but it's the same idea. Solving this system of equations will give us our a and b values if the solution exists. There are cases when we solve system of equations, if you remember, where you get a no solution. So, don't assume, always try. And so a little bit of work on the side. This is another algebra problem within your calculus problem. We would be kind of setting these up. And whenever I solve systems of equations, I always like them in standard form to start off with. So you'll notice that I moved everything on the left and right, or I just switched the order. 2a plus b equals negative 3. And we could definitely play around. Looks like I think elimination might be kind of key. So this might be me. Maybe more than one way to do this, but if you multiply the entire equation by a negative 1, the numerator's not the numerator, the top equation is going to be the same. But we will have a negative 2a minus b equals positive 3. Then a little solving. See that the b's not divide out, they cancel out. It's getting late. Got one more example after this. I'm going to stay fresh. So we have 7 plus 3 is 10. And you go through this and we say, oh yeah, we have negative 5a equals 10. Aha. That's very nice. It comes out really good. We have a equals negative 2. You guys want to find the b on your own? You can. I'll follow through. I'll just plug in a to either of the 2 equations. I'll just choose the equation in the second equation. 2 times negative 2 plus b equals negative 3. Negative 4 plus b equals negative 3. So if you add 4 to both sides, this is sometimes where we get tired, how the calculus messes us up. Like a lot of times if you mess up here, it's like really minor math, but it does make a difference. We should get b equals 1. So if we look at this, okay, so a little conclusion here. We were trying to answer who's A and who's B. We had a solution that exists. So if I want to address the final part of the problem, therefore, if A equals negative 2 and B equals 1, F would be continuous everywhere. We actually got clear solutions. And it is coming out nice. I mean, we picked these examples to work out very nice with these integer A and B's, but you know, don't be surprised. You don't need integers. You could have decimals, fractions, but there's a lot of complication going on. So what does that mean? You can kind of leave this here, but you could kind of say, what should the function end up being? So your actual function, your piecewise function, we have the x plus 10 already. We knew that. As long as x is less than -3. We had the -3 as long as x is greater than 2. But we were dealing with what do we have to write there for all the values of x in between -3 and 2, including -3 and 2. And remember, it was ax plus b. So again, if we're looking at A was -2 and B was 1, your line would connect those two pieces. Now, don't just be satisfied with the fact that you got a really pretty answer. Let's make sure that this is consistent with what we thought. So if you go back, the quick sketch that we drew just to interpret, remember, we're looking at y equals -2x plus 1. This is a line with a negative slope. So go back and kind of look at the quick sketch, and when you're looking at what could fill up the yellow part, yeah, it is very possible that it looks like we're getting an answer that's making sense with what is supposed to occur. If you got something with a line with a positive slope, or maybe you accidentally switched around the A's and the B's, that's something to question. This is very, very valuable in calculus. When you think you're done, always look back and ask yourself, did I answer what the problem wanted? Or also, is my answer making sense? So that's a really nice problem to kind of help with understanding continuity. It kind of gives you a chance to apply your one-sided limits and knowledge about being continuous. So we're just building on everything here. So go ahead, practice on WebAssign. There'll be some nice opportunities. I realize that you can use algebra to figure these numbers out, but if you were ever asked on a quiz or test to demonstrate it, we would expect you to be using calculus. So be careful on that. You could definitely use algebra to back you up, just like we kind of did in the past. Okay, one last concept. It's kind of a longer section, but it all makes sense in the long run. We're going to bring back to the front of our mind the idea of intermediate value theorem. And this is an intuitive idea that you probably already have down, but we have to kind of go into the specifics about it. That's what kind of people find confusing. So we have a theorem, and it's more something that we've taken from all our studies in mathematics up until this point. We've played around with behaviors of functions. If you have an idea about continuity, and I should probably be a little bit more specific. I kind of typed it out, but be careful. When we kind of talk about f being a polynomial, a rational function, a root function, trig function, or any combination of any of these functions, we know as long as we are in the domain of the particular problem, that f is continuous in all of those points. So I like to be careful, because if you're a rational function, rational functions are not continuous everywhere, but if you are defining the domain of the rational function, it will be continuous at every point in its domain. So I kind of want to make sure that you're clear on that. So when you deal with intermediate value theorem and they talk about f being a continuous function, a lot of times they're going to give you a closed interval. So you would want to decide, is the closed interval within the domain of the particular function in question? And then usually the answer to that is probably yes, if we're playing with you. I'll just be honest, we ask you questions, and a lot of times we set it up so that the hypothesis of the theorem usually works out. So there's kind of three components to to this hypothesis. Remember, we kind of talked about this with the delta epsilon definitions. When we look at the first part of a theorem, they're kind of setting up the if part. And as long as those criteria are true, we call it the hypothesis, or hypotheses if you want to be plural. As long as we can prove those items in that first part, then we have the then part, or the conclusion. Then you can state that the conclusion is true according to the criteria of your function, or I should say theorem at this point. So in order to kind of go through this, I think this is what I think the third formal proof that we're going to be doing in this class. I want to describe, whenever you're reading a theorem, a lot of times they speak in generic form. Sometimes it really helps to draw pictures so that you can see this clearer. So the first thing I'm going to try to approach is the letting f be continuous function on the closed interval AB. So I kind of like to break this up into 3 different pieces. So item number 1, if I were to draw any random function, I'll draw an interval between A and B. X equals A, X equals B. Here's part of my function. And we don't care, we know stuff might happen beyond it. You know, it doesn't matter what's happening beyond the A and the B. They just want us to look at what's going on between our closed interval. So corresponding X values to corresponding Y values. We're only looking at that piece of the function. So I'll undo that. I just want to make it cleaner in the picture. There we go. Okay, now the next part we want to be dealing with is they want to talk about n, and they're just using a random y value. It's any number in between the function evaluated at A and the function evaluated at B. So as long as we have these 2 y values not being equal, so we don't have a constant function. So a lot of times when I'm seeing function notation, I like to demonstrate it on my picture. If I look at A and then the function evaluated at A, remember I just go up to the function, I go to the y-axis, that would be the location of the y value, f of A. Similarly, I go to where the function is located, I go over to my y-axis. This would be the location of wherever the y value evaluated at B. Or X equals B, Y equals F of B. So I want to make sure before I start with the n, sometimes I do this in a couple different orders, but we can switch these around. We're going to try to demonstrate F of A and F of B. We want to make sure, item number 2, that these y values are not equal. They're not the same y value. And when we look at our graph, no, they're not on top of each other. One's bigger than the other. F of B is higher than F of A. So with that criteria, what they're trying to do is they're trying to set up, let's look at this n. And what we want to show or want to make sure we're clear about is that n, I'll do this in orange, n should be any number between these values. So maybe I'll look at that third criteria. Okay, so pick anywhere you want. Sometimes people don't call it n, they call it c. That's kind of going to be the relationship. Let's see. Oh, scratch that. I'm different on my variables in my notes. Let's relook at this. N is any number between f of A and f of B. F of A and f of B are on the y-axis. Just kind of remember that. So n is over here somewhere. It doesn't have to be exactly in between. It can be closer to the f of A, f of B. So they're saying if you have a y value in between f of A and f of B, then finally, if this is the case, what's supposed to happen? This is intuitive. You probably already know what's going to happen. If you travel back to your function, you find where it's located and you find the corresponding x value, that corresponding x value is supposed to tell you that, they call it C, the function evaluated at C is that value, n. So in other words, your function crosses through n. The y value equals n at x equals C. And I know in, is it pre-calculus? I know in college algebra for sure, we deal with this with showing something's a root. And it is more intuitive. If I can kind of take a side note here for a second. And, you know, we talked a little bit about polynomials and, you know, we'll go from here. So just kind of a side note, we have ourselves a parabola or some sort of polynomial. And if you're trying to show that you have a root, by the way, so sometimes they call that C. If x equals C is a root, they call that a 0 and x-intercept. The y value, f of C, should be 0, i.e. x-intercept. And intuitively, you know something crosses the x-axis. This is what we're trying to get at here. If you could figure out a y value on the function that's below the x-axis, and there's also a y value on the function above the x-axis, and you're in the neighborhood of your point in question C, well, if you can find a negative y value and a positive y value, it must be true that the function has to be crossing through the x-axis. And that's kind of what the intermediate value theorem came to be, I think, when you were dealing with college algebra. And I believe we might have some applications in WebAssign with that. I kind of like that one better, but I show you the more interesting one for purposes of lecture and discussion. So one more time, if I can reiterate, we're looking at trying to show that the function evaluated at C is equal to this value. So if you have a value in between f of A and f of B, as long as your function meets the 3 criteria, or continuous on the closed interval, what's supposed to happen is that function evaluated at C, oh, what am I doing? I don't want to cancel that out. I want to highlight it. They're just trying to tell you that your function should be crossing through y equals n somehow. We'll let that sink in. It's not always automatic. I have to do a couple of these to play around with so I can really interpret. I always like to refer back to roots because those are the ones I understand a lot more. But let me show you. We'll go through this. Last example of the section. I know this is a long one, but hang in there. We're going to prove, another proof here, that there is a number k such that the function evaluated at k is pi over 10, and they're giving us the fact that the function itself is a parabola, f of x equals x squared. So just remember, whenever we do proofs in this class, a lot of times what we're trying to do is we're trying to prepare you for the university. You move on to a little bit more of a higher division mathematics, there's going to be proofs involved. So we always like to go through the first few things, hypothesis. You know, we try to show that all 3 things are satisfied, and then we can state whatever our conclusion is. So what I like to do for myself before I'm setting up my proof is I kind of want to do some side notes to think about what's happening. For the first part, if I'm looking at item number 1, item number 2, I'll start off with labeling what's my proof. PF for proof. Nice little abbreviation. The they're telling us who the function is already. So if I look at my intermediate value theorem, they're already setting up the item number 1. We're trying to restate, is the function a continuous function on a closed interval? So let's make sure. Parabolas, y equals x squared is continuous everywhere. So the first thing I'm going to state for myself, and you don't have to number these out, I'll try to color code it for you, that f of x is a polynomial and continuous everywhere. Continuous. When I say everywhere, I can say all real numbers, negative infinity to positive infinity. But we want to talk about a closed interval. So what I'd like to do for myself is kind of, they are giving me a strange value, y value, f of k equals pi over 10. If I really want to understand this, and I have my proof, let me write my notes on the side. Let's kind of think. Let's talk about some thoughts again. Little less involved than our delta epsilons, but let's kind of have some thoughts. What's pi over 10? If I type this in on my TI, I don't know it off the top of my head. Do you? Maybe you do. But I'll type it in, pi divided by 10, just so I can have an idea of, what am I looking at? I'm not graphing this, excuse me. I am calculating it. So we have something that looks like, kind of looks like the number pi. It's just divided by 10. Aha. I should have known that. I shouldn't have needed a calculator. Oh, well. Not bad. We'll go back. We'll share again. Okay. Hang in there. We're almost done with this part. So let me share the screen again so you guys can see. So pi over 10 is approximately equal to 0.314159. Kind of like pi. 3.14159. So what I'd like to do is look at my theorem, and I might want to be dealing with, I want to find 2 y values such that they're bigger. One of them's bigger than pi over 10, and one of them is smaller than pi over 10, based on my picture here. So remember, the way we're looking at it is f of c is our f of k part. Okay. So my thoughts. I want values. Item number 1, f of x. I want this y value to be greater than pi over 10. And item number 2, I want f of x to be less than pi over 10. Basically, I want you to be above pi over 10 and below pi over 10. Now, make your life easier. Remember, our function is f of x equals x squared. Don't go crazy. Just try to figure out, if we're looking at our y-axis and we're looking at our function, if 0.3.14159, excuse me, let me go back. Make sure I am sharing. Give me 1 second. Sorry about that. Reshare. Sometimes I switch off and I want to make sure you all see this. Let's try this one more time. There we go. Okay. Maybe you didn't see what happened, but everything blanked out on my screen. Okay. So just kind of consider this number line wise. If you're on the y-axis and you're equal to 0.3 about, let's do this. What if we're 1? 0.3 would be located about here. 0.314159. So let's be nice to ourselves. We already know that that's a number between 0 and 1. So why don't we choose those as our y values and x values? So let's look at this. Let's be able to look at choosing maybe y equals 0, y equals 1. And sometimes that's a little nicer with our particular functions here. So I care about something that's bigger than pi over 10. So that would be the y value of 1. And I kind of have to think a little backwards. If I'm y equals x squared, then in order for me to get a 1 back, that means I have to look at, f of what equals 1? Well, 1 squared. So here's my first one. F of 1 equals 1. That's bigger than pi over 10. And what's smaller than pi over 10? I want my y value to be 0. Well, I have to think about this. F of what gives me 0 if I'm dealing with my y equals x squared? And I go back and say, oh yeah, well, we got lucky here. F of 0 equals 0. So play around with function notation. What's the difference between y values and x values? They happen to be the same on this part. Make your life easier. Just try to picture this. Okay, so here we go. So what am I looking for? If I'm trying to understand this, I have two things going on. I've got my y values and I've got my x values. The first thing I'm trying to state for myself is my function continuous on a particular interval. And these are speaking about x values. So we already know it's continuous everywhere, but we want to state on our particular interval. F of x is a polynomial, so it's continuous on negative infinity to positive infinity. So f of x must be continuous on the closed interval 0, 1, or 0 to 1. It shouldn't be 0, 1. Okay, so again, remember, I'm looking at my x-axis. I'm trying to restate formally. It's closed on that particular interval. Where did I get those x values, 0 and 1? It was based on the y values that I chose. I had to figure out what they were first. They happen to be the same. It's not always the case. I just tried to keep my life simple. I don't want to come up with crazy x values and y values. Okay, so that's criteria number 1. Now, what I'd like to do is kind of have some sort of statement that the function evaluated at those endpoints, f of 0, f of 1, I want to make sure that those are not equal values. And according to what our statement is, they aren't. So the function evaluated at 0, it's not the same thing as the function evaluated at 1. If you want to play with this y equals x squared business one more time, just so that you guys can see. Here's your function. Your function evaluated at x equals 0 is 0. Your function evaluated at x equals 1 is 1. So those y values are not the same. So we want to make sure that we're clear about this. We also want to make sure that we are stating item number 3. Those two y values that we just chose, we are clear that our pi over 10 is in between those on the y-axis. Okay, so profound. I know there's a lot to this. I know it's the end of the section. Hang in there. Maybe you want to take a break before you come back and rewatch this. But just remember what I did. I tried to color code. Step 1, really justify why are you a continuous function on the particular closed interval. It took some thoughts to figure out who the closed interval was. Item number 2, we wanted to make sure that they were clearly different y values. We're able to justify that with the function in our x values that we chose. And the item number 3, we want to show that the pi over 10 is clearly between our two y values, the function evaluated at 0 and the function evaluated at 1. That's what our thoughts were on the side. Now that all 3 criteria is stated, or are stated, now we can invoke the conclusion. So exciting. So by Now that we satisfied the hypothesis by the intermediate value theorem, or the cool kids call it IVT, there is a number K. In the interval. And notice we're just restating our conclusion. The open interval, so in our case, the x value 0, x value 1, such that the function evaluated at that k value is equal to pi over 10. And that is the end of the proof. Oh, that is a lot. I know it takes a little bit of thought. What I really want to emphasize with you with proofs is making sure you're clearly setting up your proof so that you're justifying why all of the hypothesis would be happening according to the values that you've chosen. And once you state the criteria of the hypothesis in the context of your problem, you can then conclude everything. So I wish you the best of luck. Go into your WebAssign, play around. I believe they're asking you more about roots, so you might have a better time with the concepts with the zeros and stuff. Hang in there. I know this is a tough concept to really take in, but the more you look at it, the more you practice, it will come second nature. So again, practice, practice, practice. And I'd like to congratulate you for getting through the chapter. It's your first chapter in calculus. So I will see you in the next chapter.